But now I'm going to introduce Alan Stern. You know, it came out of my interview yesterday with Elon. Between the two of us, we worked out what is now the slogan of the Mars Society, which is where there's a will, there's a way. And and no person better proves that than Alan Stern. Okay, I first met Alan Stern, I guess, in the early 90s, and he had this crackpot idea that we should send a probe to Pluto because, you know, we'd gotten to Neptune and, you know, you got to get all 9. And and he fought for this, basically single-handedly convinced the space community to do it. And then he did it, led a team that accomplished this. So he is now the man who has gone further than any man has gone before. And so what better way to bring this conference to a climax than to hear from the man who did that. So give Alan Stern the floor.
Thank you. Thank you, Bob. That was a wonderful introduction. And thank you for inviting me here this evening. It's a privilege to come and talk to the Mars Society and share the story of this farthest exploration of worlds. And I have to say, Carter just gave a fantastic presentation. I was listening to the whole thing as I listened to many of the plenaries this morning. And Carter, great job. I think I'm going to share my screen now. And
you are sharing.
Okay, you ought to be able to see PowerPoint. Carrie, maybe you can let me know when you see it.
We see it now, and you sound great.
Okay, thanks on both. Okay.
You're welcome.
I'm going to give you a whirlwind tour of the story of New Horizons and some of the things that we discovered along the way. And let me thank Bob for the kudos about being able to get the United States and humankind to Pluto. But I have to say, it's a team, all space flight is a team sport. In the end, 2,500 men and women worked on New Horizons, primarily during the development phase. And every one of them deserves credit for making this happen. Just as many, many thousands, if not tens of thousands of people will get credit when we send humans to Mars for being a part of that project. All right, let's dive in. And I had a little trouble advancing slides. There's the first slide. This is a pair of pictures of myself in front of the New Horizons launch vehicle and inside the nose cone of that rocket with New Horizons above me on the right, very early in 2006, just days before we launched. And I show this pair of images to say, for those of you who don't know me well, I've had the great privilege of working on very many space missions in my career. I've been on the science teams now of 30 missions, from suborbital to orbital to space shuttle missions to interplanetary missions. And I've had the great privilege of being PI of one type or another on 14 missions. And New Horizons is absolutely my favorite, without a doubt. And how could it not be? I think for all of us who worked on this project, to be a part of a first mission to a new planet is something that planetary scientists and the engineers and technicians and others that put these missions together is something that we all crave. It was the gold standard in the 60s and 70s and even the 80s to be a part of those early first missions, first to Mars and Venus with the Mariners, and then on to Mercury and Jupiter and across the solar system with Pioneer and Voyager, all the way to Neptune. And for all of us who worked on this, I have to say, we often say to ourselves, it sounds like science fiction, but it's not. We built a spacecraft that journeyed all the way across our solar system to explore the farthest worlds ever explored in the history of humankind. And that's probably a record that won't be topped for a number of decades. I hope to live to see not just humans on Mars, but also robots back to the Kuiper Belt, even an orbiter of Pluto, and the exploration of other worlds in the Kuiper Belt. but that's the subject of another talk. In any case, this has really been an epic journey of many billions of miles and now many years since we began. I'm only going to be able to talk about some of the very top level details of this project and what we learned. But with David Grinspoon, I wrote a book called Chasing New Horizons that's available everywhere. And if you want to read more about it, that's probably the best way to do it. 220 pages of goodness that tells much of the story that I can't even go into tonight. But you might wonder, and a good place to start is, how did we get to do something like this? How did we get to lead this project and carry it out? And I have to say, it was a long road, as Bob was alluding to. It actually started in the summer of 1989, when Voyager was finishing its last exploration at Neptune, when a group of young scientists, very much like the Mars Underground of the early 80s, a group of young scientists in the late 80s dubbed themselves the Pluto Underground and began lobbying NASA to build and fly a spacecraft to Pluto. If we'd had any idea how long it would take to succeed at that, we might not have started. Because as you see in this graphic, there were quite a number of instantiations of attempts to get a spacecraft off the drawing board and on into construction to fly to Pluto, or even two spacecraft in some cases. And it took us all of the 1990s and a whole series of cancellations and into the early 2000s before New Horizons was born, which is the only one of this series, of course, that ever got off the drawing board. But I worked on every one of those, as did many other people in the scientific community, the engineering community, and at NASA headquarters. And it really was a difficult slog. Every time we thought we were close, something would happen. Either something in the political winds would happen, something in the budgetary winds would happen, or a change in fashion in the way NASA does missions. Or at one point, we were very close to getting a new start, and Mars Observer blew up just days from reaching Mars. And the NASA administrator of the time decided to take the money that would have gone to start mission to Pluto and begin the Mars program that we know and love today. In any case, it was a long haul. And I'm showing now, I'm sure this looks very pixelated and blurry. This is the very best image of Pluto ever made before New Horizons. It's not much. I was PI of this program with the Hubble Space Telescope in the mid-1990s. At that time, we knew that Pluto was going to be a fascinating object. We knew that it had an atmosphere, that it had a giant moon, probably formed the same way that the Earth-Moon system is formed. We knew that Pluto had interesting surface markings, and these images, this one and others like it by the Hubble, back in the mid-90s, just after the Hubble repair, allowed us to actually see it for the first time as anything other than a point of light. But still, you can't do much with an image like this. You really don't have the resolution to learn very much about your target, and that's why we go to these places, is to put our cameras and spectrometers and other sensors up close and personal, where we can really write the textbook about these worlds. Now, how did we get this mission from the interesting A-list to the very top of the A-list so that it could receive funding in such a competitive environment as the NASA planetary program? Well, what really made the difference is the story of scientific discovery that I want to tell you now in the next couple of slides. When I went to school, when I was a grade school student and learned a little bit about our solar system, and probably when most of you did, you learned that the solar system's architecture consisted of 4 rocky planets on the inside, down close to the sun and surrounded by an asteroid belt. And then beyond that, on much larger orbits, are 4 gargantuan gas and ice giant planets. And beyond that, there was this odd footnote called Pluto, discovered in 1930, that didn't fit either the pattern of the terrestrial planets or the giant planets. and which was a real head scratcher. And from the time that Clyde Tombaugh discovered Pluto in 1930, all the way until that Voyager encounter in 1989, and even a few years beyond that, this was our understanding of the architecture of our solar system. But it was completely wrong. We thought the solar system had two zones, the terrestrial planet zone, the giant planet zone. But beginning in the early 1990s, telescopes here on Earth began to discover Pluto's cohort, another population, really the third zone of our solar system, called the Kuiper Belt. This is a view looking down on the solar system of actually discovered Kuiper Belt objects, where the dots out beyond that outermost circle, which is the orbit of Neptune, the dots represent those individual objects at their actual locations. And you'll notice among them, there's some larger ones. The larger dots represent larger objects, Pluto being the one down here, if you can see my cursor, at roughly the 6 o'clock position. I'll say more about that in just a moment. But this discovery of the Kuiper Belt that began in 1992 with just one discovery, and then the next year with 4, and the following year there were 10, and now there are thousands of objects that paint out the Kuiper Belt's architecture that have shown us there is a third zone to our solar system. It is the Kuiper Belt. And it is, this is a 3-dimensional view, if you will. It's a side view of that same distribution of large and small objects. And from the ones that we have discovered and an estimate of how much of the surface area of the Kuiper Belt we have surveyed, we know that we've only scratched the surface. We've only discovered the tip of the iceberg. Of the thousands of objects that we have discovered, it is predicted that there are actually hundreds of thousands. And we have also discovered that not only is this the largest structure in the planetary system and the third zone of our solar system, but it is teeming with dwarf planets. Pluto is not a misfit. It was simply the first and the brightest of these discoveries, the easiest to discover. But there they are. There's Eris and Makemake and Haumea and Sedna and Quoar and many more in this new third class of planets, which we call the dwarf planets. They're just smaller planets, just like the sun is a dwarf star. And it was this discovery of the Kuiper Belt and its implications for the origin of our solar system and the realization that there's a third class of planet in our solar system that we had never been to, despite decades of planetary exploration, that led the very first planetary decadal survey in 2003 to catapult the priority to fly a mission to Pluto and on beyond Pluto, deeper into the Kuiper Belt to study small Kuiper Belt objects, to the very top of the funding queue. And Congress listened, and the administration listened, and the result is the funding that made New Horizons possible. But actually, New Horizons was selected not because of that decadal survey, but a couple of years before, hoping that the decadal survey would make this decision. NASA put out an announcement of opportunity. A series of teams formed, including our own, and competed to win this mission to Pluto and the Kuiper Belt. And we each wrote big, thick proposals, roughly 1,000 pages of engineering, cost, and management. Those were judged against one another. And fortunately, our proposal, this is the cover of the New Horizons proposal back in 2001. Fortunately, our proposal was selected. That was in late November of 2001 when I got a phone call from NASA headquarters saying that New Horizons was the selected team. And the result was that all of us who had promised to go and build this spacecraft and get it launched ended up in a kind of a whirlwind 4-year project to do what took Voyager and most other planetary missions 6 to 8 to, in some cases, 10 years to do, which is to design and build and test and get a spacecraft to the launch pad. We only had 4 years and 2 months to do this. And to top it off, to make it harder, we only had 20% of the budget, 2 dimes on the dollar of what it took to do Voyager. So we had to invent a whole new way to do this. We had to break the price mold. We had to break the schedule mold. And those 2,500 men and women that worked on New Horizons really rose to the challenge. It was 52 weeks a year and 7 days a week for those entire 4 years and 2 months. And I could tell you stories, but we don't have time about the commitment that it took. But I will remain in awe the rest of my life of the people who worked behind the scenes to get this together and to bring it to the launch pad. This is a cartoon view of the New Horizons spacecraft. For reference, that dish antenna, the high gain antenna, is about a little over 2 meters in diameter. That sets a scale for you. You can see the names of the 7 scientific instruments on board. There are color and panchromatic imagers, medium and high resolution telescopes, ultraviolet and infrared spectrometers, radio science, plasma spectrometers, and a student-built dust counter, the first ever student-built instrument to fly on a spacecraft. And that is something I'm very proud of, because now it's become the norm in planetary science to include those kind of payloads built by students at universities and operated by students at universities on very many planetary missions. This is a picture of New Horizons down in Florida shortly before we put it on the rocket. This picture is a great one in my view, because not only can you see the spacecraft without all of the multi-layer insulation on it, so you can see the superstructure, you can see some of the scientific instruments like this one and that one. You can see the radioisotope thermoelectric nuclear generator that powers our spacecraft, just like Voyager, Cassini, Galileo, the pioneers that also traveled too far from the sun to use sunlight. And there are people there for scale that show you this spacecraft is barely the size of a baby grand piano, yet it contains not just the 7 scientific instruments, but all of those flight systems and redundant copies of those inside that box to make this entire journey across our solar system. The other thing that you may not realize, but looking at this image, there's only one spacecraft there. You know, when Pioneer 10 and 11 were launched to be the first to Jupiter, it was still in the days when we had the luxury of being able to fly 2. Same for Voyagers 1 and 2, but in the case of New Horizons, we just didn't have the money to do it. So we had to build in enough reliability to do it with only 1 try. And we rose to that challenge. And even today, nearly 15 years after launch, New Horizons is operating flawlessly, and so are all 7 of its scientific instruments. So one of my favorite pictures of New Horizons, on the day that we fueled the radioisotope thermoelectric generator, Friday the 13th of January, 2006. That's myself standing in front of the spacecraft, which is inside the nose cone of our Atlas V launch vehicle, inside its hangar at this point. And that's the day that we really began the mission. Even though we didn't launch it, that's the day that New Horizons became electrically live, and we began operating it from our Mission Control Center in Columbia, Maryland, at the Johns Hopkins Applied Physics Laboratory. And it wasn't very long, just 6 days later, that we launched that spacecraft on that enormous Atlas V, which gave us a flawless ride to Earth orbit, and 40 minutes later, used the Centaur upper stage to take us out of Earth orbit onto an interplanetary trajectory, and then lit a custom-built Star 48 solid rocket motor that was inside the nose cone beneath New Horizons to boost our orbital speed and energy to take us out to Jupiter for a gravity assist that would speed us on the way to Pluto. And the combination of that enormous launch vehicle, that solid rocket motor for a 4th burn, and the Jupiter gravity assist is what allowed us to cross the solar system in record speed in only 9.5 years. Let me give you a feeling for how fast New Horizons left the Earth. At the end of the burn, of that solid rocket motor from that time until we reached the orbit of the moon was not the 3 days of Apollo, roughly 90 hours, but only 9 hours. We launched at 2 in the afternoon on Thursday, the 19th of January, and by 11 p.m. that night, Eastern time, the spacecraft had crossed the orbit of the moon, about 10 times faster than Apollo missions took to reach the orbit of the moon. And we're still traveling at that high speed, boosted, of course, by Jupiter's great gravity. Here's our route of flight. The launch, as I said, in January of 06, Jupiter flyby just 13 months later. Compare that to Galileo, 6.5 years to reach Jupiter. Compare that to any of the more recent Jupiter missions. Cassini went to Jupiter and took 4 years to do it. We did it in 13 months, and then on across the great gulf of the middle solar system, the orbits of the giant planets, on an 8-year journey that basically spanned the two Obama administrations until we reached the Pluto system in July of 2015. And there's Pluto's orbit in yellow, and you see that our trajectory, the red line with an arrow at the end, crossed Pluto's orbit just as Pluto was crossing the plane of the solar system. On our way, as I said, we did a Jupiter gravity assist, and this was the only object that we flew by along the way. These are images from that flyby, from the cover of Science magazine, what I call Rolling Stone for nerds. This is Jupiter and its volcanic moon Io in color, as seen by New Horizons. We had a tremendous scientific flyby of Jupiter in January and February and early parts of March 2007. But moreover, that flyby, besides being scientifically rich and our gravity assist to take us to Pluto, was also the flight test of most of the software that we used at Pluto for target tracking, image motion compensation, all of that we needed, and we needed to work. So this flyby served all 3 of those purposes, and it just worked out flawlessly. And then we flew on for those 8 years, which I will skip here, and take you right to the flyby of Pluto in 2015. Here, the larger image on your left is at the Johns Hopkins Applied Physics Lab, just outside of our mission control. That's Glenn Fountain, who was our long-term project manager for New Horizons. And in the inset in the upper right, you see our mission control with one of our flight controllers there. And then one thing I want to point out about this flyby is, although all of the great data that we collected was all of the really high resolution images, the high resolution composition spectra, the atmospheric data, everything else that you see in textbooks and everywhere else on the web, for example, everything that I'll show you was collected in just a couple of days around the closest approach, which was on Bastille Day, the 14th of July. The actual flyby was a 2-year-long flight operation that began 6 months out with optical navigation, imaging, with course corrections to hone our course to Pluto, and then was followed after the intensive data collection with 16 months of data downlink back to the Deep Space Network antennas on the Earth to get all the data that we collected back to Earth. And to give you a scale, the amount of data that we collected at Pluto was about 100 times as much as a Voyager flyby tape recorder load. So a tremendous amount of data by first flyby standards. And I also wanted to show you the geometry of the flyby. The Pluto system is like Uranus, tipped over on its side, and it was basically pulled on to the direction of our flight. And so we pierced the system with times there shown in hours on the morning of the 14th of July, essentially perpendicular to the orbits of Pluto's 5 moons, Charon being the large moon, and then the 4 small moons that orbit outside of Charon. We had very difficult navigation challenges to meet in order to fly through the shadows of Pluto and Charon and watch the sun set and rise and the Earth set and rise for the occultation experiments. But our navigators and our flight control team carried that off perfectly. In fact, after a 9.5-year journey, New Horizons was only 86 seconds off course. And I'm very proud to say we were 86 seconds early. This is an image of our main target, Pluto, in the lower right, with its large moon Charon next up to its upper left, and then 2 of the 4 small moons. That's Hydra and Nix in this family portrait made by New Horizons. This is in true color. But most of the pictures you see now, like this one, are in enhanced color, where we've, in the computer, driven the color up to the rails. We've stretched the color for the target so that you can see the contrast between redder and bluer or yellower areas on the planet or on its satellites. This is the binary pair, Pluto and Charon. For reference scale, Pluto is about 3/4 of the distance from the United States west coast to east coast. And Charon, which is not to scale in this image, it's bigger than its actual scale, so that you can see more detail, is about the size of the state of Texas. And of course, when you look at Pluto, you can immediately see that it's very different from Charon. It's brighter, it's more colorful, it's got a greater degree of surface geology variation. It's got that giant heart on the surface, which I'll talk more about. That's a giant nitrogen glacier, which we have since named Sputnik Planitia. Sputnik for the first satellite. In fact, one of the naming themes on Pluto, which I nominated, and really our whole team nominated, but I asked for, was that in completing the reconnaissance of the classical planets known at the birth of the space age, I wanted a naming theme to honor pioneers of space exploration, pioneering missions, pioneering teams, and pioneering individuals. And so Sputnik, the largest feature that we see on the flyby hemisphere, is named for the very first and most pioneering robotic mission ever, the Soviet Union's Sputnik, first satellite in Earth orbit. Here's a close-up view of Pluto images in a mosaic that we wrapped on a sphere as if we were flying above Pluto ourselves. This is the view you would get if you had the eyes that New Horizons had flying along that trajectory. And you can see mountain ranges and a little bit more detail down on the glacier. You can see giant fissures emanating from Sputnik. These are tectonic faults, if you will, caused by the giant impact that created the basin in which, the impact basin in which Sputnik lies. And I just wanted to show you this behind the scenes picture if you haven't seen it before. It was taken by a New York photographer named Michael Soluri, who I invited to join our team shortly before launch. And he chronicled our team and its activities from before launch really to this day today, even out in the extended mission. And this is, I just love this shot because it's candid. It's really at the very moment that some members of our science team were seeing the first high resolution picture of Pluto in our science analysis room at Johns Hopkins on the morning of the flyby, a couple of hours before this image was released in a press conference that we did that morning. And you can just see the emotion in the room. And I love it because for all of us who work so long and so hard to get a mission to Pluto, and then to compete for a mission to Pluto, and then build it at breakneck pace, and then fly it across the entire solar system with only one shot at getting this right. I just can't tell you how much this meant to all of us. But you can see how excited those people are. There are many images like this, and many images of high fives and hugs and so forth at this flyby and at our subsequent flyby in the Kuiper Belt. And some of those will be published next year in a book by the University of Arizona, but I only have time to show you this one. Here's Pluto in true color. You can see the geologic complexity across the surface. You can't see its atmosphere, but it's there. It's made mostly of nitrogen. It's at pressures and temperatures that are very similar to the Earth's upper atmosphere and the mesosphere. There's that giant heart, the glacier Sputnik Planitia, and also dark regions called maculae. Here are two of them. This one's called Cthulhu, informally, and there are 5 more, and we've given names to all of them. Some of them are on the far side. Here you can see more of the tectonic features, including a great rift valley stretching north and south, probably also associated with this impact basin. But I'm going to show you close-ups and give you a feel for the stunning geology on Pluto's surface. So before I do that, I should say that Jeff Moore at NASA Ames, our planetary geologist who leads our planetary geology team, has called Pluto the new Mars. And I thought it was particularly appropriate to mention that here for all of you at this Mars conference. I won't have time to point out the many similarities between these 2 different red planets. But as I walk through the next half dozen or so slides showing you some details of Pluto's geology, many of you will recognize that from glaciers to heavily cratered terrains to young terrains to some of the activity features that I'll show you on the surface, they all have analogs on Mars, virtually every one of them. So let's take that tour. And I want to start with this beautiful view of snow-capped mountains on Pluto. I live in Colorado, and of course we have snow-capped mountains. These mountains way out in the Kuiper Belt are not snow-capped with water ice. That bright ice at the top of those mountains, which by the way, are about as high as the Continental Divide here in the United States. And this scene, since it doesn't have a scale bar, is about the size of Western Colorado. But those bright snowcaps are actually made of condensed methane. That's CH4, or the natural gas that's used in heaters and some kitchens here on the Earth. But at Pluto's temperatures, it's a solid, and it condenses out and plates out on the tops of very tall mountain ranges on Pluto. Here's another individual place on Pluto, and if you're wondering where each of these places are, there's a context image, and the little green box within the bigger green box shows you where on Pluto we are. This is just showing you very heavily cratered terrain, and because it's very heavily cratered, we can be sure that this is a very old terrain, which we have age dated through techniques of crater retention age to about 4 billion years old, about as old as the planet itself from the birth of our solar system. Very old terrains, and right next to it, out on the glacier, we see young terrains where there are no craters at all, which we can't age date because we don't see any craters to date it with, but we can set an upper limit age of only 10 million years. In fact, those individual ovoid and semicircular cells that you see are convection cells in which the nitrogen ice is overturning due to a thermal gradient in the glacier, a vertical thermal gradient. And that erases craters as they're formed. And the best models we have indicate that those individual cells turn over about once every million years, maybe even every 500,000 years. And so that's probably the real age of this surface that we're seeing, which is 10,000 times younger than the these places on Pluto that are very old. We also see evidence of enormous avalanches where snow falls or runs down valley chutes out of these mountain ranges, again, 4 to 5 kilometers above the glacier, just here on the left, and pool out on the plain. In this case, pool about 50 miles across, or a little bit larger. So enormous avalanches of material. And here again, you see no craters, so this avalanche was in the geologically recent past. But if that's not enough, we find cryo-volcanoes and other sorts of volcanic constructs on the surface at a number of different places. This particular cryo-volcano is about the size of Mauna Loa on the Earth, about the same diameter and about the same height above the surrounding terrains. It is enormous, and you'll notice there are no craters on its flanks, so it is also young, created in the geologically recent past. It's named Wright Mons after the Wright brothers, pioneers in aviation. And here's another type of terrain, a hooler that terrain in an area several hundred kilometers across off the eastern side of Sputnik and Tombau Regio, which we call bladed terrain. Each of these blades that you see that are aligned are made of methane ice, and they are probably condensates out of the atmosphere. They run for hundreds of kilometers. How they are organized to be aligned like this, we think has something to do with sublimation processes and the action of the faint sunlight warming the terrains, even if feebly. But in addition, each of these blades is about 1 kilometer high. So if you were standing on the surface, you would see them stretching up thousands of feet in your sky, and to your left and to your right, stretching over the horizon. And in fact, as I said, hundreds of kilometers. This is a type of terrain that's very prevalent, not only here on Pluto, but also on Pluto's far side, and which has no analog anywhere else in the solar system, a completely unique type of terrain. We even see evidence for at least one paleo lake, this one about 25 kilometers long with a distinct shoreline, and we know from stereo imaging that it sits in a hanging valley in mountains to the west of Sputnik Glacier. And we know from compositional mapping that that lake, at least the surface of it, is made of condensed nitrogen. But you can't have liquids on Pluto's surface today. The temperature and pressure just don't allow it. The temperature and pressure are below the triple point of nitrogen where liquids can exist. So we think this is forensic evidence that attests to a previous era in which Pluto had a much thicker atmosphere, much like Mars had a thicker atmosphere in its ancient past, and much more abundant liquids on its surface. Pluto apparently had both running and standing liquids, but not water, nitrogen in this case. Just an absolutely geologic wonderland, a world with complexity far beyond its size gives it any right to have, and which, because of its current day activity, from avalanches and cryovolcanoes to this vast overturning glacier, Sputnik, which is about 1 million square kilometers, larger than the state of Texas on the Earth, and yet is active today, indicates that somehow Pluto's geologic engine, unlike the Earth's moon and many other small worlds in the solar system, Pluto's engine has not run out. And how it is powered today, 4.5 billion years after formation, how it powers such vigorous geology after all this time, is a mystery that still hasn't been solved. And I think it'll take an orbiter to go back to really learn how that geology is powered. And now let me close on Pluto with this set of images from the highest resolution strip from the North Pole down onto the glacier, in which we can fly over Pluto's surface as if we were in a very high-speed airplane and travel more than 1,000 miles from the North Polar regions caked in snows of nitrogen, over heavily cratered terrains in which you can see layering beneath the surface, to dust devil tracks in the snow, onto badlands, and then very large water ice mountain blocks covered in a veneer of nitrogen and methane. And then onto the shoreline of Sputnik Glacier, in which you see dune fields, convection cells, and other phenomena, including wind streaks, that just attest to the range of geology that you see across Pluto. What a spectacular world we found at the other end of the solar system. And then we went on. As we were charged to do by the Decadal Survey, New Horizons was built to go on with the power and the communications capability and the warranty, if you will, the design for life, to go on deeper into the Kuiper Belt, to fly by at least one small Kuiper Belt object, these so-called planetesimals that are the building blocks of the planets. And the value in this is not just pure exploration, that's one value, but the real scientific value is that this region of the solar system, being so far from the sun, is both cold and undisturbed. And that Kuiper Belt object that we flew by, named Arrokoth, which means sky in the Powhatan Indian language of Maryland, is the most pristine object ever explored by any spacecraft, 4.5 billion miles from the sun, and kept in this deep freeze near absolute zero for all these billions of years as a kind of archaeological dig, if you will, into the history of the building block, the history of formation of the building blocks of our solar system. That flyby, as it says, took place on the 1st of January, 2019. Arrokoth was discovered by us after a 4-year-long search for a flyby target within our fuel reach. We actually found Arrokoth along with several other candidates to fly by with the Hubble Space Telescope, and traveled another 3.5 years and more than 1 billion miles to reach it in early 2019. There's a depiction of our path across the Kuiper Belt after Pluto. But I want to give you a feel for just how difficult this task was. Beyond finding this little needle in the haystack, let me run this very short 8-second video. It's going to zoom up on Pluto onto Sputnik Glacier and then place Arrokoth for scale. Have a look at this. Down on the glacier, and boom, there's Arrokoth. This little target, no larger than the scale of a county here in the United States, which has a reflectivity that's so dark that it's almost draped in velvet and only lit by the sun at 44 astronomical units, so several thousand times fainter sunlight than we see here on Earth on a bright sunny day. All conspired to make the navigation challenge to hunt this little guy down and in a one-shot, get it right or go home flyby at almost 35,000 miles an hour. New Horizons succeeded again and brilliantly. And I chalk that up to the team of professionals, the flight controllers and engineers, and the science team that runs it, and all of those folks that help build it and get it launched. It's just an amazing piece of American workmanship. And I'll show another video. This is a set of images made in the fall of 2018 as we were flying up to Arrokoth against the star fields of Sagittarius, where the spacecraft is headed. And you'll see Arrokoth pop out of the star field as a little faint ember and grow in brightness and move through the parallax caused by the motion of the spacecraft primarily over a period of several weeks. This is how we hunted it down. So Arrokoth, there it is, right in the center, moving to the bottom. And we can play that, I think, one more time. There we go. Here comes Arrokoth. There we go. Okay, now we'll move on. Well, like that picture of the candid picture of the team at the moment the first high-res image of Pluto appeared, this is a picture in our geology and geophysics room at our mission control at 2:30 in the morning on the 1st of January 2019, when the first high-resolution image of Arrokoth appeared. And again, you can see the team's emotional energy there. And what a weird and wonderful Kuiper Belt object this turned out to be. It's really taught us such a great deal. Meet Arrokoth. Here are high-resolution images of it. I just have a few to show you. It is a contact binary. The two lobes were initially distinct objects that somehow gently came together. This is a clue to how these individual lobes formed. I'll say a little bit more about that. You see a complex geology on the surface. For scale, from stem to stern, this object is about 20 miles long, 33 kilometers to be more precise. And it's very highly flattened, which you can see in this set of tweened images made by a Russian amateur image analyst named Norman Tkachenko to illustrate from New Horizons data just how flattened these two lobes are. That's another clue to the way that Arrokoth and its two lobes individually formed. And here it is in color with a little geological map as an inset to just tell you that we have all kinds of data. They're all on the ground now from this flyby. It took a long time because the bit rates are even slower from this greater distance. So it took longer than getting the data back from Pluto, even though we took just about as much data. The bit rates were lower. And from that, we learned a great deal. I skipped ahead. I want to say what Arrokoth has primarily taught us is about the composition of the distant nebula out there where the Kuiper Belt was formed, and about the mode of accretion of these building blocks that threw away the standard theory of planetesimal accretion in favor of a much newer theory that's only been around not 50 years like the standard theory, but only about 15 years, that indicates that all of these objects were gently assembled in little local particle cloud collapse accretion mode called pebble cloud collapse, which now has become, for all intents and purposes, as a result of New Horizons, the standard theory of planetesimal formation, at least in the Kuiper Belt, but probably also down in the inner solar system where planets like Mars were formed from similarly small objects that very likely were formed by this pebble cloud collapse mechanism. I'm going to end with just a few more slides, and this is the last image from New Horizons I'll show. It's my favorite image of the entire mission. It's a true color image of Pluto, made looking back on the morning of the flyby as we flew through Pluto's shadow, and its atmosphere, which is truly blue, was backlit by the sun. And the reason I love this image so much is not for its scientific value. There is scientific value. For example, if you look closely, you can count the structure in the haze layers above Pluto's limb. But more importantly, the only way to get an image like this is to get it from the far side of Pluto. And for all of us that worked so long to see a mission funded, then built, and then flown all the way across the solar system, this was the culminating image. That's why it's my favorite. It's kind of the equivalent of the Apollo Earthrise image in terms of accomplishment. And for all of you that are working to get humans to Mars, this took us a long time. From the time that we first started a conversation to go to NASA and ask for a study of how we would possibly send a spacecraft to Pluto in 1989, until we got all the data back in 2016, it was 27 years. I know you've been working on getting humans to Mars for longer than that, but these long hauls pay off, and so does persistence. And so I want to encourage you to keep at it, because I think we're closer than we've ever been to getting humans to Mars. And I think we'll see it in our lifetimes. I also want to show you a couple of other images. This one is from our mission control. You can see the clock in the back. It's just 4 seconds to Pluto flyby closest approach back there in the summer of 2015. And I just want to say thousands of people came to this flyby because they wanted to be a part of it. People from all walks of life. And I have to say, I think this is just a small taste of what we will see when humans are ready to set foot on Mars. So is this. The fact that we were on the front cover of 450 newspapers all around the world the next morning, that we got the Google Doodle, that we were on countless magazine covers, that we were the biggest web event NASA had ever seen in the flyby of Pluto, with literally 2 billion visits to our website in 48 hours. And I think that the landing of humans on Mars and that first expedition will put this to shame. I think the entire world will watch. The entire world will be wired by the 2030s when we do this. Even those who don't have internet will soon have it, thanks to the Leo constellations that are being launched and that are about to be launched in the 2020s. And when we go to Mars with humans, I think it's going to be one of the most emotionally powerful and moving and inspiring events for STEM education and for many other purposes that we've ever seen. And I'm very proud that the flyby of Pluto could be the biggest event of its time, but I'm sure that it'll be dwarfed by what the first expedition to Mars does. Let me also say to all of you, keep at it, because the other red planet besides Pluto beckons, and it's time to get serious. And I'm so happy to see that Jim Bridenstine this morning made such a call and such an emphasis on going to Mars once we practice at the moon. It's around the corner now. I can feel it, and I hope all of you can feel it. And thank you for letting me talk about the exploration of Pluto and the Kuiper Belt by New Horizons and the New Horizons team. So back over to you, Bob, and if there are any questions, I'd be happy to answer.
Robert, do you want to present questions to Alan?
His microphone is muted. Go ahead, Lee.
Okay, so we do have a few questions for
No.
you here, Alan. Thank you. Oh, here we go.
I'm unmuted.
Okay.
Okay, no, I'm here. Okay. To Alan Stern, have we found, or what are the plans to find a second Kuiper Belt object to fly by?
That's a great question. We have not found one yet. We have about an eighth of a tank of gas left, the hydrazine in the spacecraft propellant tank. Coincidentally, that's about as much delta V capabilities it took to do the Arrokoth flyby. We just started the searches for flyby targets and other scientific targets in the Kuiper Belt this summer in June, using the giant Japanese Subaru telescope on top of Mauna Kea in Hawaii. This year, as a result of those searches, we found 73 Kuiper Belt objects along our path, many of which we can study with our telescopes and imagers, but none of which are close enough to reach. Now, don't be discouraged, even though we know it's a long shot to find one before we leave the Kuiper Belt. We're going to look under every rock. It took us 4 years to find Arrokoth, and we're not going to quit after one season of looking for the post-Arrokoth target. So stay tuned.
Okay, Jerry Stone from Great Britain writes, my name's on the New Horizons spacecraft, so I designed a bumper sticker. It said, my other vehicle has gone to Pluto. So he says, is Pluto a planet?
Well, you know, just take a look at it. I like to use the Star Trek test. That's the simplest way to determine what's a planet. You know from watching Star Trek that when the starship shows up at a new place and the viewfinder and the bridge comes on, you pretty well know if they're orbiting a planet or an asteroid or a star or an alien spacecraft right away. And but all kidding aside, the geophysical planet definition, which is the definition that most planetary scientists use, calls anything big enough to be rounded by self-gravity that's not so large that it's doing nuclear fusion like the sun. Anything that's big enough to be rounded, what we call a planet. And Pluto way qualifies for that. It's actually about 10 times the diameter of the smallest objects that qualify. That means we're going to have a lot of planets in the solar system. We better get used to it. We can look up their names in a book. There's no need to memorize them. Pluto is what got us really thinking about what it means to be a planet. It sent the astronomers in a tizzy back in 2006. They still haven't gotten over the fact that there are an astronomical number of planets, but planetary scientists have. And when you go to planetary science meetings, or you look in the planetary science literature, you see everything from Pluto and its kin in the Kuiper Belt to large satellites like the Earth's moon and Titan and Ganymede and Triton and many more called planets. And so by planetary science standards, you better believe Pluto is a planet. And I'm very happy that it's also the real number 9.
Okay. Do the 2 lobes of Arrokoth have a name? Arrokoth have a name?
Arrokoth's lobes do not have a name. And in fact, neither do any of the surface features in the sense of an official name. We have individual names for surface features that we use informally, but we haven't yet submitted names for surface features on Arrokoth. We just refer to the 2 lobes as the small lobe and the big lobe, and that does just fine.
Ahmad writes, he says, could there be a black hole near the solar system? And let me just amplify that. Could there be other unexpected types of objects near the solar system?
Yeah, well, I don't know enough to know firsthand whether there could be black holes, tiny black holes in interstellar space that are currently within the distance of the Oort cloud and therefore within the solar system or not. I know that there are some scientific papers out there on that, but I'll be honest to say I haven't read any of them, so I can't really judge. But today with Google Scholar, you can go out and judge for yourself. So find those papers and take a look. To answer Bob's question, I'm sure that there are many types of objects that we have not yet discovered, particularly in the Kuiper Belt and the Oort cloud. The Oort cloud is what I often call the solar system's attic, because all the objects in the Oort cloud were ejected there during the final stages of clearing of the giant planets. And I'm sure there's a wide range of exotic objects. Most provocatively, there are probably small planets or even mid-sized planets like Mars that were in the game in the inner and middle solar system, formed with all the rest that we see today, but which were ejected out there to this great deep freeze, and which we will someday find. I think that census will be largely complete at the end of this century. But today, we have to only speculate. The great thing about the planetary astronomy ahead is that all those discoveries are going to start with this new generation of telescopes, the extremely large telescopes coming online in the 20s and then the 2030s. And I just can't wait to see what's out there.
Are we sure that all these objects in the Kuiper Belt and the Oort cloud were created with our solar system? Could some be from other solar systems?
It's an excellent question. When solar systems form, including our own, computer models show that clearing of giant planet regions ejects objects not just to Oort cloud-like structures on the lip of their gravitational potential well, but also throws many more objects out into interstellar space than get deposited in Oort clouds. And even though our Oort cloud is estimated to have between 100 billion and 1 trillion objects in it, many more objects than that were cast out into interstellar space. And every solar system with distant giant planets should be doing the same thing, or should have done the same thing in the past. So interstellar space should be teeming with all kinds of exotica, asteroids, comets, equivalent of Kuiper Belt objects, dwarf planets, large planets, black holes, and brown dwarfs for that matter. And from time to time, the larger objects and the rarer ones come through our solar system. And then the smaller objects, like interstellar comets, come through all the time. We just began discovering those. And so stay tuned on those discoveries too. We're just at the very beginning of this era.
1 minute.
Okay, basically, several questions are basically asking, how far can we go with current technology? Can New Horizons reach the Oort cloud? Could another probe with current technology reach the Oort cloud?
New Horizons, if its health continues, can probably go on to about 100 astronomical units out, which is not yet the Oort cloud. We're going to run out of power on that RTG, which has a half-life and produces less power every year. We're going to run out of power by 2040, maybe even a little before that. But with current technology, it's possible to build missions that go even faster than New Horizons and which operate longer. And so, for example, today there's a mission called the Interstellar Probe, which is on the drawing boards. And if it's highly rated in its decadal survey, it'll get built and launched perhaps a decade from now and wants to travel out to 1,000 astronomical units. And I am also part of a startup company called Helicity Space that's looking at a new technology for fusion drive that could take us out to way beyond 1,000 AU and do it with technology that's essentially ready today in the laboratories. It's much easier than creating fusion power, in fact. And I don't have time to talk about that because I think my time is up, but we do have the technology to explore much farther out than we have, and I hope to live to see that.
Okay, thanks a lot, Alan. That was great.
Thank you, Bob. It's a pleasure.
Okay.